Hello and welcome to this presentation. My name is Dwight Burford and I am a research professor at the University of North Texas. This presentation is on a new friction stir process called Submerged Bobbin Tool tunneling technology, or SBT tunneling for short. The initial SBT development work occurred off campus during the first half of last year, and an initial tech transfer evaluation was completed this past summer. The contributors to the summer tech transfer portion of this research are listed here. My co-PIs for this work were Dr. Manzo and Dr. Siller, both of UNT, and each of the 4 graduate students listed contributed significantly to the work being presented today. There are 3 main parts to this presentation. The first provides a description of SBT tunneling and its potential for innovating product design and manufacturing. The second part features highlights from the initial development stage, and finally, the third presents results from the tech transfer evaluation conducted this past summer. The path from development to tech transfer evaluation is illustrated in the graphic. The work was begun off campus on a Haas TL1 lathe. It was then transferred to campus for testing on an MTI RM1 friction stir machine and a friction stir link friction stir welding end effector mounted on an ABB IRB 7600 robot. SBT tunneling is based on a unique tool set design that has a bobbin-shaped probe. The shoulder on the terminal end of the probe is then passed through the workpiece as the process progresses. This is illustrated schematically in the left figure, which shows a cutout around an advancing SBT tool. A side view of an SBT tool set configuration is illustrated on the right. Like a conventional bobbin tool, or BT, used in friction stir welding, an SBT tool set has 2 opposing shoulders spaced apart along the bobbin or probe section of the tool. Unlike conventional BTs, however, SBTs are used to form enclosed internal channels by the shoulder located at the terminal end of the bobbin being submerged within the workpiece, while the opposite shoulder rides along an outer surface of the workpiece. Also, like other BTs, the opposing shoulders of SBT designs serve to contain a significant portion of stirred material generated throughout the progression of the process. As a result, process forces produced parallel to the tool's axis of rotation are reacted between the opposing shoulders. Therefore, compared to single-sided tool designs having one shoulder, SBT tooling produce relatively lower out-of-plane forces that must be supported by tooling fixtures, potentially allowing them to be less complex. In turn, fabrication equipment for internal channel production by SBT tool sets have reduced force and stiffness requirements compared to equipment for single-sided friction stir-based channeling methods. With this innovation, then, new opportunities exist for utilizing production CNC equipment for broadly deploying this new technology on existing machining centers and industrial robots. Incorporating the SBT process with machining operations opens opportunities for completing parts in a single setup, including producing curvilinear subsurface integral channels in complex shaped parts. SBT tool sets are designed to form integral subsurface channels or tunnels within components having internal pathway requirements. Example tooling uses are in heat exchangers, cooling plates, and tooling in general, for example in vacuum tools. Example structural components include smart structures, battery trays for transportation vehicles, integrally stiffened beams and spars, and parts incorporating lightweighting designs. Internal pathways or enclosures may be for access ports, composites for inserts, gases, fluids, powders, sensors, tubing, and wiring. Existing approaches for forming internal pathways include machined channels with cover plates attached by fasteners, adhesives, welding, for example friction stir welding, stamped and extruded sections, tubing and/or piping attached to a metal plate by brazing or by mechanical constraints through being pressed into machine slots. Two existing friction stir-based processes are friction stir channeling, or FSC, and TWI core flow subsurface machining. SBT tunneling is a versatile process. Channels are manufactured in situ and may be installed in confined places as shown in the figures below. It is a rapid process. For example, well-formed channels have been produced in 6061 aluminum at travel rates of 25 inches per minute. SB tunneling may also be performed on machining centers as part of a series of operations. Note, however, that SBT is not a machining operation. It is a thermomechanical process that depends upon process parameters in a much different way compared to machining operations. SBT channels may be used with or without inserts, like wiring with potting materials. With inserts, SBT channels can serve as conduits for wiring and tubing. Without inserts, SBT channels may serve as standalone pneumatic and/or coolant lines. An example of the versatility of the SBT process is shown in the illustration on the right. It is of an idealized modular out-of-autoclave vacuum tool having internal pathways for heating and cooling fluids. It incorporates a couple of other uses of integral subsurface channels, including vacuum lines and channels for thermocouple wire management. Such active heating and cooling features are used in a variety of components and equipment. These range from basic heat exchangers and cold plates to advanced components such as electric vehicle battery trays and structures for dense electric components and components designed for reduced heat signatures. Channels can also enable the functionality of part actuation and monitoring by providing integral pneumatic lines and pathways for distributing wiring for health monitoring devices, respectively. The curvilinear part featured on this slide is another example of this versatility. It incorporates integral channels as conduit for tubing and as a way to route wiring to sensors and other devices such as proximity sensors. Embedded sensors may also be incorporated for measuring accelerations, vibrations, and perhaps impact, ambient gases including humidity and vapors from volatiles, distance measurements such as by lasers, loads and strains, and pressures in fluids and gases. This idealized component is also intended to illustrate the benefit of the trim profile of SBT tool sets. This characteristic of SBT tool sets allows them to place internal channels offset from irregular surface in close proximity to raised features as shown. Other advantages noted on this slide include the reduction of weight in monolithic structures, ones in which the channels cannot be extruded by conventional processes, for example. New structures having integral composite stiffeners with embedded health monitoring sensors are further examples of advanced uses of SBT integral channels. In the second part of this presentation, highlights of the development phase of the project are featured. As noted previously, the work was begun off campus during the campus closures which occurred in the first part of last year. Based on this preliminary work on a Haas TL1 lathe, an initial evaluation phase was conducted on two purpose-built friction stir systems located at UNT's Discovery Park. The last part of this talk will feature results from SBT channels produced on these two systems. Before presenting those results, we will now review the genesis of SBT tunneling. SBT tunneling was originally pursued to develop an agile, low-force approach to fabricating curvilinear integral pathways in a single pass. Due to the closures of the labs on the campus this past year, for health-related concerns, this development work was initiated off-campus on a 2D prototyping system. The main components of this 2D system included a standard Haas TL1 lathe and a custom fixture designed and built previously for friction stir tool development. This unique testbed was ideal for driving the development of SBT tunneling toward a low-force friction stir process. A brief summary of some tool and coupon development details are provided on this slide. As noted, the work was begun on 6061 T6511 extruded bar, ranging in thickness from 1 inch down to 3/8 of an inch in thickness. A starting hole and slot along the process path were machined in the coupons for flash control and for dimensional stability of the channels. At least 8 generations of SBT tool sets were designed and built to obtain channels nominally between 2 and 2.5 millimeters in height by 9 millimeters in width. The results in this presentation are all from the 8th generation tool design. Since this is a standard CNC tool room lathe without force control capabilities, all SBT channels were produced under position control. Once the coupons were positioned and the axes zeroed, SBT channels were formed in a series of coupon sets. For a given set of development coupons, the travel speed along the path of the channels was increased from as low as 1 inch per minute to as high as 25 inches per minute. In the early phase of the development work, tool breakage after processing several coupons was not uncommon due to the probe incorporating a significantly sized bobbin tool shoulder at its terminal end. A series of probe features were then varied until a robust tool design was demonstrated to produce multiple channels in a series at high travel speed. As noted on the slide, the plunge was carefully controlled, followed by a dwell to obtain a well-formed channel at the initial stage of processing. The dwell was then followed by a carefully controlled ramp-up to the steady-state travel speed along the channel path. Also note that in all cases, the transition to the steady-state travel speed occurred in less than an inch. Examples of 4-inch long 6061 coupons mounted in the FSP fixture on the Haas lathe are shown in this slide. The picture on the left is of a 3/8 inch thick coupon being processed on the fixture. The picture on the right is of a 5/8 inch thick coupon after processing to form a channel. A cone is formed on the exit of the tool at the end of the path. This is caused by the extraction of the bobbin-shaped probe and can be easily removed in subsequent machining operations. Coolant was applied to the anvil as shown to dampen thermal fluctuations in the fixture and thus reduce thermal expansion and contraction swings in its components during processing and the subsequent cool-down phase. As part of documenting the quality of SBT channels, coupons were examined visually, metallographically, and by way of the AMPI X-ray microscope at Discovery Park, which is shown in the lower left. In the upper left image of this slide, the front and back sides of a coupon processed at 25 inches per minute is featured. As shown in this image, slots were machined in both sides of the development coupons to visually inspect the completed SBT channels. The image on the right is of a different coupon processed at 24 inches per minute. Both the upper and lower first surfaces of the exposed channel were found to have the appearance of a machined surface, having semicircular striations similar to the shoulder track on the top surface. On the next couple of slides, XRM results are provided for the 25 inch per minute coupon shown here in the upper left. On the left side, you can see the 25 inch per minute coupon mounted in the XRM. On the right are X-ray images taken of the coupon. It will be noted that no voids were found in the friction stir process zone forming the top or ceiling of the SBT channels. Examples of the surface quality obtained from the XRM are shown in the next slide. The XRM proved quite valuable for documenting the nature of the SBT channel surfaces through providing visual images like this one and by generating typical measures of surface roughness. As you can see, the surface is regular or periodic. Slower travel rates were found to produce closer spacings in the surface roughness periodicity. 3 coupons were then sent to extrude hone for abrasive flow machining, or AFM, of channel surfaces. Here is the set of 3 coupons that received a range of abrasive flow machining treatments. The internal surfaces of the channels appeared to have been smoothed significantly by the AFM operation. Optical and XRM examination are yet planned for this set of coupons. In the third part of this presentation, highlights will be presented of the tech transition portion of the SBT development project conducted this past summer. First, results from the verification runs carried out on the MTI RM1 friction stir welding machine will be reviewed. And finally, results from the runs performed on the friction stir link friction stir welding end effector will be presented. A set of 5 SBT tunneling coupons were processed on UNT's MTI RM1, and the same process parameters developed on the Haas TL1 lathe were used for processing this set of coupons. The only parameter that was varied was travel speed, which again ranged from 5 inches a minute to 25 inches per minute. This set of coupons was pre-machined to match the coupons used in the development phase of the Haas TL1 lathe. Here is a picture of this set of 5 SBT tunneling coupons, which were processed at 5, 10, 15, 20, and 25 inches per minute, respectively. All exhibited smooth shoulder tracks and minimal flash. From a previous slide, the graph to the left shows the process sequence in terms of travel speed. Note how the ramp up in travel speed is achieved in less than 1 inch for each coupon. As previously noted, this sequence was followed to produce a sound ceiling over the channels. It was also developed to form consistent channel dimensions from start to finish of the SBT process. Also included on this slide is a schematic of the set of coupons shown in the previous slide, each of which has an SBT channel of 3 inches in length. Note how the schematic shows that the slot does not extend all the way to the entrance hole. This gap in the slot helps the tool shoulder heat the material just ahead of the advancing tool as it begins to ramp up to the steady state travel speed. The size of the gap affects process forces. Therefore, the size of the initial contact area of the tool shoulder must represent a balance in shoulder heating and process forces. The next 4 slides show the axial forces measured during SBT tunneling in coupons processed at 10, 15, 20, and 25 inches per minute, respectively. This slide shows the force plots for the 10 inch per minute coupon. The forge force for the steady state portion of the process is about 700 to 800 pounds. The longitudinal or transverse force was nominally 250 to 300 pounds, shown in negative values. And the transverse or cross force was less, at nominally 50 to 200 pounds. The initial transient segment of the curves relates to the transition from the steady state hole to the slot along the SBT process. It also relates to the thermal softening that occurs in the ramp-up phase. It appears that the force plots follow the travel speed plots on the prior slides. This slide shows the force plots for the 15 inch per minute coupon. The forge force for the steady state portion of the process is nominally between 800 to 1,000 pounds. The nominal longitudinal force is approaching 500 pounds, and the transverse force was less than nominally 100 to 300 pounds, again the force values tend to follow the travel speed plot. This slide shows the force plots for the 20 inch per minute coupon. The forge force for the steady state portion of the process is nominally around 1,000 pounds. The nominal longitudinal force is nearly 500 pounds in absolute terms, and the cross force was less than nominally 200 to 500 pounds. And finally, this slide shows the force plots for the 25 inch per minute coupon. The forge force for the steady state portion of the process appears to increase slightly, climbing nominally to as high as 1,200 pounds. The nominal longitudinal force is around 350 to 600 pounds, and the cross force was less than nominally 250 to 600 pounds. Although the force values tend to follow the travel speed plot in general, there is that indication that they may increase further. Testing on longer parts will confirm the trend. The video in this slide shows the ramp-up of a steady-state portion of an SBT coupon being processed at 25 inches. The monitored process forces from the steady-state portion of the coupon processed at 15 inches a minute are shown in absolute values in this slide. Sets of force plots like this can be used to evaluate whether a given SBT tunneling process is a good fit for a particular machining center or industrial robot. Well, what do cross-sections of SBT channels look like? An example is shown in the next slide. This set of micrographs are for the same SBT channel formed at 15 inches per minute. As with other friction stir processing operations, a fine-grained microstructure is produced in the stir zone between the channel and the outer surface. The stir zone produced by the terminal end of the tool is rather shallow and considerably less rough than the opposite channel's face. It will also be noted that no voids are evident in the stir zone between the bobbin tool shoulder, suggesting that the channels will be airtight when tested. Depending upon the application, mechanical testing like bending fatigue may be used to qualify structures incorporating SBT channels in flight hardware, for example. And now for the final part of my presentation. This part includes results from the runs performed using the friction stir end effector mounted on the ABB IRB 7600 robot located at UNT. Because SBT tunneling is a relatively low force process, we may anticipate that 2D and 3D channels can be produced on industrial robots. A series of coupons like those tested on the MTI machine were processed with the friction stir link end effector. The relatively low force readings from the MTI ARM1 machine suggest that the robot-based system would be capable of producing out-of-plane force applications. Several other factors were also weighed as part of this evaluation, including the tooling. By deploying SBT tunneling on robotic platforms, we see an opportunity for new cooling channel applications. Another potential opportunity is to maintain and repair existing channels. The next several slides show a series of SBT coupons processed on the ABB robot. The very first SBT coupon run on the ABB robot is shown on the left. As expected, the tool deflected from the program path at the start. Training of the robot occurred, and the second attempt at the run was successful in terms of the machine following the program path. It was also observed that the robot was programmed to over-plunge in anticipation that the shoulder might not fully engage with the surface. In the next run, the overplunge was lessened, but still needed to be reduced in subsequent runs. A major observation was that even with the overplunge, the SBT tool set produced a channel. This result showed that the process is robust and that it can accommodate some deviation from the nominal process parameters. Next, SBT coupons were processed at 10 inches a minute using the friction stir link end effector. The same coupon is shown in both pictures on this slide. Very little flash was observed on the coupon, which was easily removed by hand. The distortion in the exit hole gives a sense of the lateral deflection of the robot due to process forces. SBT coupons were also processed at 15 inches a minute and 20 inches a minute using the friction stir link end effector on the ABB robot. Again, the process path was found to be nominally straight, and the little flash that was observed on the coupon was easily removed. The exit hole again gives a sense of the side deflection of the robot due to the process forces. U-shaped channels were then run at 5 inches per minute and 10 inches per minute. This slide is for the first attempt at running a U-shaped channel. As observed in the image on the right, the robot deflected to the side of the path due to processing forces and some programming issues. From the MTI testing, the forces would have been less than 500 pounds for a 5 inch per minute travel speed. Correcting the program real time, the robot was able to track the machined slot in the coupons. Here are pictures of the same run at 5 inches per minute after the tool turned the corner and finally when the SBT tunneling process was complete. This coupon and one run at 10 inches per minute were then sectioned to examine the channels. The 5 IPM coupon especially gave us the opportunity to examine how the channel may have been affected by the robot straying from the anticipated process path. The sectioned U-shaped coupons are shown in this slide. As marked, the 5 IPM coupon from the last couple of slides is shown on the left, and the 10 IPM coupon is shown on the right. Cross sections of these coupons are shown in the next slide. Without going into too much detail, this slide shows that the channel formation was adversely affected by the tool when it deviated from the slot that had been machined into the coupon prior to performing the SBT tunneling operation. Even so, a channel was produced throughout the travel length of the run, once again showing the robustness of the technology. This concludes my presentation on the development and tech transfer evaluation of the new SBT tunneling technology developed at the University of North Texas. We are currently conducting client research on different aluminum alloys used in aerospace. If you have questions or comments about SBT tunneling, feel free to give me a call or to send me an email. You can help us by identifying alloys and channel morphologies to pursue next in developing this new technology further. My email and office phone number are listed on the next slide. Thank you for your attention. This project was funded by the Advanced Materials and Manufacturing Process Institute, or AMPI, which is located at Discovery Park on the UNT campus in Denton, Texas. In case the font on my card is too small, my email is dwight.burford@unt.edu. My office number is 940-565-4523, which rolls over to my cell phone after a few rings. Thank you again.